This is Lab 7, Thermal Conductivity. Okay, this is our basic setup here. We have the steam generator. It comes up through a copper pipe and then goes through this little Tygon tubing, which is then attached to this metal box down here. This metal box is the steam chamber. The steam goes in here, it condenses inside the steam chamber, and then as it condenses, it leaks down here into this collection facility. On top of the steam chamber is a glass plate. This is this little glass plate right here. Not all of you will have glass plate. Some of you will have other kinds of plates. But we've got, on this particular one, I got a picture of a glass plate. It's got a little rubber mount on it. The glass plate, this is the material that we're measuring the insulating value of. Okay, so this, when we talk about the thickness of it, that's the thickness that you have to measure. On top of this, and I don't have it in this picture, we're going to have a mold of ice that's going to be sitting there. That ice, as steam goes through here, is going to melt, and it's going to drip down into this container here. And we're going to measure the mass of this container, or the mass of the water melting it. And from that, we're going to find out the insulating value of this property. So we're going to be using this equation, delta Q over T equals Ka delta T over delta X. Rearranging it, we're going to solve for K. Let me see it rearranged there. This delta X is the thickness of the material, and you're going to have to measure that. So that has to be measured in the lab. A is the area between the material and the change in temperature. The area is going to be the area of the ice block. Okay, and you're going to have to measure the diameter of the ice block and then calculate the area. T is simply time. It's how long the ice block is sitting on the material. So you're going to be melting the ice on top of the platform. It's undergoing a phase change. And the formula for latent heat is this guy. And this should be an M, not an N. It's M. Q equals MLF, where LF is the latent heat of fusion for melting and freezing, which I'm giving to you. And for water, it's 334 kilojoules per kilogram. Notice this is kilograms. Substituting in, we get this K equals M, where M is the mass of the ice melt. 334 is that latent heat of fusion going from ice to water. Note that this thing is going to have to be in kilograms eventually. Delta X is the area, the thickness of the material, not the area, but the thickness of the material, and that's going to have to be in meters. T is time. Time is, of course, going to be in seconds. A is that area. It's going to have to be in meters squared. And 100 is the change in temperature. And we're going from ice, which is at 0 degrees, to steam, which is at 100 degrees. So that 100 is just delta C or delta K. Okay, you need to put this background, at least this stuff, in your lab book. So get that. Pause the video and write her down in the lab book. As I mentioned, you need to write the background in your lab book. Oh, and don't forget, write the background in your lab book. Okay, so we're going to be measuring and recording delta X. So delta X, again, is the thickness of this plate, this glass plate. And again, it's kind of hard to see in this picture, but it's going to be that glass plate. You're going to mount the insulating plate on the steam chamber. So here you can see the thumb screws are off. And you're going to take care, once it's mounted, that the glass plate, this thing right here, this edge, is flush against the water channel. And this right here is the water channel. You want to make sure that the water leaks out. And then you're going to be tightening these thumb screws down here to keep it securely in place. The manufacturer, Pasco, recommends putting a little Vaseline right in here between the channel and the sample to make sure that you get a good seal so you don't have water leaking down here and not into the cup. And again, not all of you will have glass. Some of you will have different material. You're going to verify before you start up that there's a styrofoam cup right here, and it's lined up to collect the water coming out of the water channel. So again, we're going to have the ice cube right in here. And as the ice melts, it's going to go right down in here. You want to make sure your balance is on and that it's tarred so that you don't have to worry about measuring the mass of the styrofoam cup. It's going to be 0, and you're going to be getting just the mass of the water that's melting. You want to make sure the steam collector has some place to drain to, okay? And that the steam generator way over here out of the picture is actually hooked up to the steam chamber. And that should be done for you. I'm going to be going ahead and doing that before you come into class. So here we can see there's another view. We can see the steam generator coming out here, and it's hooked up to the steam chamber. And again, that should be done for you already. You're going to turn the steam generator on, which is basically your hot plate. It's going to take a little bit of time for the steam to start up. I'm going to try and have them so they're kind of pre-warmed a little bit. But you're going to let it stabilize. Make sure that it's actually boiling water and that things are working well, and the steam chamber has a little tiny bit of drainage coming out of it. Not a lot. While it's getting stabilized, you're going to take the ice out of the mold, set the smooth side up, and measure its diameter. Record this in your lab book under data as, of course, the diameter D. Place the ice still in its mold on top of the insulating plate, letting the ice slide out as the experiment proceeds. You're going to calculate the surface area between the ice and the insulating plate and record it. One partner can be doing that, and another partner is going to be making sure they're taking the mass measurements of the melted ice every 30 seconds and recording it. So again, we've got that water dribbling into the cup. So starting at time 0, you should be recording what that mass is. And you're going to let it run for 6 minutes. Write a brief summary of the procedure in your lab book. Dimension, write a brief summary of the procedure in your lab book. You're going to need data tables in your lab book also, so you want to put those data tables in there. The insulating plate description, what kind of insulating plate I give to you, what its thickness is, units in meters, what the diameter of the ice is, and what the area of the ice is. So that's the area between the ice and your insulating plate. So you're just going to need one table to record that. Then you're going to need another table that goes on for 6 minutes to record the mass of the melted water. So get those tables in your lab book. Did I mention you should write the data tables in your lab book? Don't forget to get the data tables in your lab book before you come to class tomorrow. The data analysis is going to be unfortunately more complicated. To begin with, it's not too bad. You're going to calculate the K for each of your times. So you're going to go back to the background information that you have written in your lab book and look at the data that you have written in your lab book and calculate K. Then we're going to start doing some error analysis. You're going to look at all the instruments you used. So how did you measure the diameter of the ice? How did you measure the mass of the melted water? Okay, and you're going to determine the precision of your measurements. So that's one thing that you're going to do. The next thing you're going to do is graph the value you obtained of K versus time. So time is going to be your independent variable and K is your dependent variable. Do it on the computer. You can use either Plotly or graphical analysis. Be sure and print out the graph with a line of best fit. Also, don't forget to save it just in case you need to go back in. Don't forget to label columns and label the graphs as you should. Okay, and then using that line of best fit, you're going to write an equation for this graph. And you're going to use this, the graph and the equation, to evaluate your error. You're going to use that as a tool. The next analysis is going to be a statistical analysis of the data we have for K. So remember, you did this with the density data. That means you're going to find the mean for your data. That's easy enough. It's just the average. You're going to find the standard deviation for your data. Remember, you can go back and look at how we did that for the density data. And you're going to find the standard error for your data. Again, go back, look and see how you did it for the density data. So you're going to have 3 ways of looking at error. You're going to have this second one, third one, and fourth one. And finally, somewhere in there, you're going to get the known value of the insulator that you used from me, Mrs. Hedden. And you're going to determine the percent error between your mean, your average value for K, and the known value. Percent error is theoretical, which is the known value, minus the experimental, which would be your average, divided by the theoretical. And you're going to take all that and multiply by 100. Next, you're going to be doing a typed conclusion, 1 per group, that you'll be presenting to the class. In this conclusion, you should look at each of the error evaluations. Remember, there were 3 different types. And compare them to the percent error and explain if they were dependable for predicting the error that you actually obtained. The conclusion that you hand in and have ready for presentation should also include all of your data, your sample calculations, the graph that you created, and the analysis results. So while you will be doing your data taking in your labs, so in your lab books, you're going to be writing this down in a rough form. In your lab books, well, not in your lab books, you're going to be graphing this, so this won't be in the lab book per se. You're going to do this, so this should be in your lab books in rough form. And this percent error, okay, so you've got this data analysis in your lab book in a informal format. That means it can be a little bit sloppy. But in a formal format, so it should not be sloppy, you're also going to have it in a typed conclusion. So that's the analysis results that will be in the typed conclusion. The graph you're going to have in the typed conclusion. Do one sample calculation for each thing. The data should be in a typed conclusion. And in addition, you're going to have to discuss how these 3, so what 3 do we have here? Number 2, dumbest instrument rule. Looking at that graph and looking at the equation, and I want you to try and figure out how that graph will help you to figure out your error. And statistical error. You're going to use those 3 methods and say, well, this was my actual percent error. How did my actual percent error compare to looking at percent error using the dumbest instrument rule? How did my actual percent error compare to analyzing the graph? You're going to have to think about what analyzing a graph will mean. How did my actual percent error compare to the standard error I found using the statistical method? Have fun. There are no quiz questions with this video, just the video. And getting everything written in your lab book before tomorrow. Thank you very much for your time.